Hello, I'm Pam Hoffman, Everyday Spacer.
I'm Jeff Miller, 2049 Outfitters.
At Everyday Spacer, we show regular folks how to personally and directly participate in space exploration, science, and astronomy. We're here on Friday nights at 9 p.m. Pacific Time, 12 midnight Eastern Time, and 2 p.m. on Saturday in Queensland, Australia. We're broadcasting live from Thousand Oaks, California. Last week's trivia question was, what was the original name for brown dwarfs?
Oh.
Hey, Dawn.
Hey, Dawn.
Welcome. I wonder, do you know that, Dawn? What's the original name for brown dwarfs? Because Jeff found it, and here, I will go over here and talk about it. They were called black dwarfs, and it's kind of interesting because he talks about it was theorized by Shiv S. Kumar in the 60s to exist. They were originally called black dwarfs, a classification for dark substellar objects floating freely in space that were not massive enough to sustain hydrogen fusion. Isn't that interesting?
Oh. Hey, Scott.
Hi, Scott.
Doing pretty good. I always cough for a few weeks after I've been sick, so here I am coughing. But yeah. I feel great. Thanks.
We're having fun.
Thank you, Scott.
You're up. Oh, forgot to look it up. Well, now you know. It was called a black dwarf. I figured you might know that.
Yeah. Okay. Tonight, sorry.
We're going to do that tonight.
A little bit of a cough.
Yeah, both of us.
I even got her with it. Tonight's topic is Redshift Wrangler.
Nope.
Oh, that's the other show. It's Redshift Wrangler.
Yep.
Thanks.
Yeah,
Thanks, Scott.
Thanks a lot.
We'll be back in 8.3 seconds. Tonight we'll demonstrate another citizen science project called Redshift Wrangler. We found this on Zooniverse, though. It's funded by NASA. You can also find it on the NASA Citizen Science Projects page.
Oh, hey, Janie.
Hey, Daniel.
Oh, Daniel. I thought it was Janie. It was green.
There's Janie.
There's Janie. Hi. Yeah.
That's both.
Awesome. Thanks so much for being here, folks. We really appreciate that. Go ahead and finish.
You may remember from last week that we planned to demonstrate a brown dwarf project. This took a turn and a new twist since then.
Yeah.
Pam, tell us about the brown dwarf project and then the Redshift Wrangler project.
Yeah, this had plot twist galore. All right, so you sharing the screen. Oh, and we got comments.
Yep.
Coughs and giggles.
Yep.
We'll see about that. All right, so go ahead and share. Mm-hmm. Because when we looked on Sunday, because we set it up with a graphic and start the promoting process on Sunday night, the week, before the show on Friday, we came here, Backyard World's cool neighbors, and looked, and lo and behold, the damn thing said 94% full. We're like, what? And then I was looking at it this week, and it's 0. So I don't know what's going on. We'll see. We'll tune into that and see what's happening. But tonight, and one of the things we decided, because, that project was so complete, we're going to go looking for the projects page, and we'll start using this most help needed. And I see another comment. Go ahead.
Yeah. Hi, Cliff.
Hey, Cliff.
Yeah.
Thanks for joining us.
He
Nice.
says, hey guys, Cliff is here. Have no fear. Lost in space.
Ah, got it. And so,
Daniel says, I recently heard you can navigate underwater using cosmic ray sources as a way in a way similar to GPS.
No kidding. That is interesting. So our first stop, and now that we're going to go with most help needed, they'll be less likely to be full. We tab over to here and we look for space, and then we go and find like this one. This one looked good, so I decided to do it. All right, Redshift Wrangler is what this is called. And what you're going to do is you're going to help these scientists use the light from distant galaxies to look back in time to the early universe. And so you can learn more, but I'm going to go ahead and look at this information down here, because there's actually two parts of it, task 1 and task 2. Identify spectral features, and you're going to look for emission and absorption lines. We'll talk about what that is in a second. And the other one is check spectral fits. All right, and so they have some of these graphs. It doesn't look all that interesting, but I thought this was a pretty, there was plenty to sink your teeth into with this project. And it does need help. So I think it's a good one for citizen science out there, scientists out there to participate in, help them out. And so this was cute. A picture is worth 1,000 words, but in astronomy, a spectrum is worth 1,000 pictures. And a lot of work is done with spectral images in astronomy, and you can read all about it. They have let's see, there was some stuff in here I wanted to be sure and point out.
Spectral images. It makes it sound like they're doing ghost photography in space.
No, this has to do with, and maybe if you were in a class in chemistry, you would burn an element and then look at its spectrum. And that's actually the way that we know what kinds of things are in stars, because we know what the spectral lines look like or absorption lines. So we've got spikes or dips, and those are the different lines. So let's see. And you can absolutely read this. It's not going to be exhaustive, but it will be a good demonstration. Oh, and I like this part here. We need your help to decipher the fingerprints of light from distant galaxies and uncover how they form, grow, interact with each other throughout the history of our universe. This is funded by NASA, and you can find it over on their citizen science page as well. But we found it here, and I really like how they're, you can see them the same every single time. They've got the about, classify, talk, collect. These are the main places you can look at the different content for this. Of course, if you just want to jump right in, you can do task 1 and eventually do task 2. And I always recommend task 1 because it is the way that you can kind of figure out things, understand it. And then task 2 typically delves deeper into the project. So I went ahead and opened up an about page for you. I really, really like this about. Well, that makes sense. It's NASA, so they have a lot of great information, and they really, really lay it out for you. So it's not just them asking you for work. It's, hey, here's some good educational content as well. And so let's see. I'm gonna just browse through this a little bit. Using spectroscopy, the study of light, to learn more about distant galaxies and the early universe. This page will help you get started. Once you've learned how about light and galaxies and the cosmic timeline, you'll be ready to head over to the Classify tab and start working with real data. Let's dive in. How do we use these galaxies to look back in time? Yeah, we do a lot with spectra, actually. I mean, we can tell things like, is this moving away from us, or is it coming closer to us? And that's that red shift, blue shift stuff. We can tell what the composition is. If a planet is, interfering with the stars interfering with the planet's atmosphere, we can kind of tell, oh, there's a difference between what we saw with the star and what we see with this atmosphere. Because planets are really hard to see. They're dark. They're like just rocky things out there, and the only way we see any of them is because their star illuminates them, or they go in front of the star and it diminishes the light from the star just a little bit. All right, so let's see. Yeah, they talk about time, and yeah, I thought there was a really good one in here too. Timeline describes galaxies. Oh, okay. I really like this part too. Why should we care about what's happening far out in space? The oxygen you breathe, the carbon you are made of, and the iron that flows in your blood all come from elements in space that are part of the cosmic story of stars forming, living, and dying in galaxies. Learn about the elements in galaxies not only allows us astronomers to learn about how stars and galaxies develop, but also learn more about where we came from and our place in the cosmos. This video right here, I thought, was an excellent kind of introduction to the people involved, some of the people involved and what you're going to be doing with these tasks. They actually, the first part, I think talks about, no, that's a different video. Sorry. And it has the people and the different, like the fingerprint part, some of the spectroscopy, and then there's another video that delves into, how the different, the two parts work, the two tasks. Yeah, I see a comment. Yeah.
Yeah, Cliff says our view is so small compared to what there is out there. Spectrum, that is.
Well, the spectrum really tells us a great deal about it. I mean, when I first learned about this, I was just blown away at how just a simple spectral chart can give you so much information about the cosmos. Really, really fascinating. So it's a great project. I think it's a great project to try your hand at. There's plenty to do with it. It's got 2 tasks, and plenty to sink your teeth into. It's not super simple, but it's not real hard either. All right, so let's see. How can we even study galaxies that far away? Yeah, we use the light. You take an image of a galaxy like the Andromeda, which is this one here. Well, it's 2 galaxies. This is the Andromeda one, and I forget what the little one's called. Let's see. For our project, we're most interested in something called spectrum, or spectra if it's plural. The light from an object, a distant galaxy, is spread out in visible light. We call this a rainbow, and works kind of like a fingerprint of elements. A spectrograph on a telescope works like a prism to spread light out into a range of colors or wavelengths. So yeah, this is how they're going to observe it with this, what do they call this? A prism, but I think there's another term for it too. It's, yeah, I'll have to see if it's in here. And here's where you see these, what they look like. By looking at the spectrum of a galaxy, we can identify the fingerprints of different materials and determine what elements are present. You can see spectral features as peaks called emission lines. So that's, that's these ones, these peaks. And the other ones where there's blank here, I see color here for the emission lines and blank spots for absorption lines. And you'll see charts with both of them when we go to the task and we do the task itself. All right. Yeah, these images show matching emission and absorption spectra showing brightness versus wavelength in the images. The rainbow panel along the top is called the 2D spectrum, and the red line on the graph below is called 1D spectrum. It's like a picture and a graph, which is what they look like. All right, yeah, like I said, I mean, we're not even halfway through. This is quite extensive, and it's easy to understand. That's the great thing too. It's not super technical that's going to lose you after the first sentence. All right, how do we determine how far away galaxies are? We use something called cosmological redshift. And you have probably heard this sort of an effect, and they call it a Doppler effect, especially with a train. If a train's coming, it has a certain sound, and then when it goes past you, it has another sound because either the wavelength is being compressed or it's being expanded.
Basically, higher pitch coming towards you, lower pitch going away.
Right. All right. And they talk about trucks, but I think a train is even easier to understand. And I think a lot of us have experienced sitting at a train tracks and hearing that kind of a unique, impression of it coming and then as it's passing. All right. And it's the same thing works in the spectra in terms of light. It's not sound, but it's light. And they actually have a really good...
because it's a wave.
Yeah, it is. It is a wave, just like sound is. So as you can see, and I was like looking at these intensely, and okay, they've matched up the color parts, right? You can see the color parts here. And yet this specific fingerprint is either shifted. Well, this one's normal. If we saw something at a distance and it stayed there, that would be the normal thing. If it was moving one way, it's kind of shifted to the red, and you can see it here. They've all been moved a little toward the red. Yeah, we got another comment.
Daniel, you hear the sonic Doppler shift with jets at the airport.
Yeah.
Too. Or even a car going past you.
Yeah, good point. But I think a lot of us kind of can relate to the train because it is you're sitting there, you're waiting, you're not engaged too much elsewhere, and you can kind of tell, you can kind of you experience that Doppler shift. All right, so let's see. Yeah, so in the middle, it's not moving. The redshift, if we're moving away from us, so redshift is going away, and the blue shift is coming toward us.
Yeah, well, redshift, the waves are basically a lot, whereas this is a normal wave, redshift is more like this. And so when it's moving away from you, the waves stretch out because it takes longer for the next bit of wave to get to you.
Ah.
As it's moving away from you.
They might have an image of that. I don't think so, but...
And when it's blue shifted, it's more like this.
Yeah.
As, because as it's coming toward you, the next bit of wave takes less time, to get to you than the first bit did. So they compress.
Redshift is compressed.
The blue shift is compressed.
Because it's coming toward you.
Blue shift is compressed. Redshift is going away from you.
Redshift spectrum, move away from you. You're right. Okay.
Yeah. And
toward us. Got it.
And
okay.
The thing to be aware of is that the wave doesn't actually change. It's just you perceive it as stretched or compressed just because it's getting to you faster or slower.
Yes, that makes sense. I did see another comment come in, I think. Is that new?
Cliff, yeah. Our band that we see is way small, but in this age, the future of the technology, it will advance even faster and bounds. It looks like, just look at JWST, yeah.
Yeah.
Yeah, they use the sound effect in films quite a bit, I think.
Oh, okay.
Yeah, basically it's an audible cue that something is moving toward or away from you or past you.
Mm-hmm. Okay, so yeah, there it is. Redshift moving away from us, blue shift moving toward us. And you can see how even though these look the same and the same distance apart, they're in a different part of the spectrum. Mm-hmm. I'll have to try and remember that.
And the reason why we look at redshift is because almost everything's moving away from us. Almost
everything is, yes. The stuff in the local cluster is moving toward us. Mm-hmm. All right, so let's see. Yeah, we can actually measure the rate at which everything's moving too. Mm-hmm. All right, I'm going to keep going though. How does astronomy help us look back in time? Well, there's a relationship between how far away something is as well as how long ago. So if the farther something away is, the farther longer ago it is as well. Mm-hmm. All right, so let me just read it. Looking out of space is like looking back in time. The speed of light is the ultimate speed limit, but it still takes time to travel from one point in the universe to another. If a galaxy is millions or billions of light years away, it will take the light millions or billions of years to reach us. When that light reaches us from a distant galaxy, it may look different than when the light left. Oh. All right,
and yeah, we got Daniel has a question. I wonder if there is a theoretical upper limit to electromagnetic waves. Or do they go on to near infinity? And he says, in frequency, he means.
Right. Kind of figured.
Okay. The biggest redshift, I suppose, would be no sine wave noticeable whatsoever. But that would be moving away from you so fast or be so far away that it'd be outside of our observable universe. Mm. I mean, you really wouldn't see it like that. So yes, theoretically, it could be such a slight wave that it would take, say 1,000 years for it to reach from peak to trough as it's coming toward you. But it'd have to be moving so fast away from you that it just doesn't make sense. Again, blue shift. Again, the faster it comes towards you, the more it compresses. Theoretically, it could get to the point where the peaks and troughs are infinitely close. Well, it's not going to happen.
I'm going to give you an example of something that I learned when I was playing an instrument. Because most instruments have a lower level. Like I played flute. There was a bottom note I could reach. However, the more skilled I would be, there wasn't a top end. I could keep going up and up and up. So it's possible that is also true with something like this. I don't know for sure, but that just gives me a clue as to maybe there is a relationship between the two.
Yeah.
So yeah, I don't know.
Yeah.
Oh, it's Cliff. Okay, good.
Yeah, Cliff. Or should I say the difference between Hubble and JWST pictures, the difference spectrum that they work at. Yeah. Yeah, JWST looks at infrared.
Yep.
Which I used to think, why would I want to just look at the heat of things? But then I realized, and they actually explained it somewhere, that things that are farther away are redshifted. So, what's, green, although there's very little actually green out there, but just as an example, what's green will appear to be yellow or red if something's really far away. And so, you can color correct that back to what we normally see, so we can get some meaningfully looking images of really distant stuff. And it's not just heat maps. It's actually just an image, just so redshifted that you just correct it back over, and there you go.
All of those have been changed so that we can see them. We don't actually see in infrared. And there's actually places that you can go out there and do that kind of work yourself as well. I see somewhere.
Daniel, the upper limit is thought to be the Planck frequency. Yeah. Basically, theoretically, the smallest distance that it's possible is the Planck frequency, which is approximately 10 to the 50 hertz. This is the frequency at which the energy of a photon is equal to the Planck energy.
Okay. It's very interesting.
Here is, for the tinfoil hat crowd, the Planck constant is what they consider evidence that we're living in a computer simulation. And that's the smallest pixel. Don't know.
Dawn's got a thought too.
But experiment has shown out that the Planck's constant probably exists. And Dawn says, I think the frequency or wavelength of EM radiation is considered infinite. Yeah, but basically infinite, but gets more and more improbable as it goes out to either end. And the lower limit is 10 to the negative 30 cosmic background.
All right. We're doing good tonight.
Yeah.
That is one of the things I love about our crowd. They weigh in on this and inform us way more than we could do on our own. All right, so let's see. So we get the idea that the farther away we look, the farther back in time we're going. And I definitely think you should read this for yourself too. I don't want to give away all the fun stuff, because you should come here and play with it too. Where do you come in? They have this nice little chart that kind of goes around like this. Galaxies emit light, which travel across space. Then these telescopes collect the light from the galaxies. Astronomers split the light into wavelengths to create spectra. Citizen scientists make measurements. We, the researchers, analyze the results. So what we do here is the citizen science part, which goes back to the scientists. So this is really important stuff, people. And the scientists make discoveries about distant galaxies and the early universe. And they actually share this with us too a lot of times.
Sorry, folks. This is with cough medicine and a Ricola in my mouth.
Yeah, I think we got a couple more comments. So.
Okay.
Yeah, that one.
Daniel, it's still a very awesome simulation. A new X-rays telescope is launching this month. X-Prism, yeah.
Where is that launching from, Dawn? I hadn't heard about that. Oh, another part I love about that. You people know way more stuff than I know too. All right. So they've got two basic places that they're gathering from: the Keck Observatory and the Hubble Space Telescope. Keck is on Mauna Kea, and we actually got some news about Hawaii today. They've had some terrible wildfires there, so we're thinking about them for a while today. Here's the part. This is what I wanted to talk to you about. In this project, you'll be identifying spectral features, emission and absorption lines in a set of spectra of distant galaxies to help us find out which elements are present and determine the galaxy's red shifts. That one's going farther away.
Yeah.
All right. which most of the universe is going away from us. Each measurement you make will help us locate galaxies on the timeline of cosmic history, which is this image here. This is below. The image shows a timeline of how galaxies have looked and evolved over time into how they exist now. Each galaxy we observe fits somewhere in this timeline. You will be the one to help us figure out where. So when you make a measurement, and each one of these actually has a number of people. They didn't say in this one. A lot of times we've read 15 to 20, but the group will come to some kind of consensus, or it will have some confusion, and that's the one that the scientists will go and take a look at in more detail, so that they can understand it better, and we help them sift and sort that stuff. Yeah, we have another comment.
Yeah,
awesome.
Don says it's launching from Japan. X-Rism and Slim lunar lander.
Excellent. Thank you so much, Don.
And Daniel says X-Rism will launch on a H-11A 202
nope, that's
rocket.
2A.
Oh, 2A.
Mm-hmm.
202 rocket from
and I believe that's the rocket that's similar to Delta II. Because when I worked at Boeing in Huntington Beach, I met the man who went to Japan and helped them develop that rocket. So I think that's the one. All right, so let's see here. Yeah, so when you help out, you are going to be helping them fit where these galaxies are in this kind of timeline of the universe. All right, what else do we have? Your task. There are 2. The first one is to identify spectral features. And this one I found to be quite good, quite simple. Not overly plain and hard. It's not too hard. It's not too easy.
It's not counting craters or something.
No,
right?
It's not counting rocks. Scott. So here's the full image of this, and these are parts of it.
Probably pieces that the computer identified as potentially useful.
Well, yeah, the computer has sorted some of this, and especially in this one, you'll find out that the computer isn't always right. It gets confused with some of these. But let me talk about this, because what you're going to do is you're going to take a look at these parts here. When they label them like A, B, C, D, E, F. And you're looking for things like these little spots of brightness right in here. And also you'll see a peak with it. So remember, that's like the image versus the graph. You got a peak here. You've got a peak here. You got a peak there, and the rest doesn't really have anything like that. And the second one, I got to tell you, I did look at this. I'm still a little confused, so it's quite possible you're going to get a part 2 for this episode, because I want to understand this a bit better, so that I can demonstrate it more properly for you. But I think I'm getting there. So we do have these. First task is to identify the features, and that's these spikes as well as the brighten. And when it's an absorption line, there's a gap. And they go, instead of up, they head down. So it's kind of a steady noise, and then a peak or a trough, one way or the other. And they'll have a corresponding bright spot or a gap. And this one is to check spectral fits. And this is where the computer has decided, well, this is a thing, and this is a thing, and this is a thing, all these little colored dotted lines. And you're going to sit there and go, I don't think so. Or, yeah, that's right. The computer got it right.
So probably giving them feedback to the computer to help train the computer.
Yes, you're helping to train the computer. And like all
kind of at work where they ask you to train your replacement.
Yeah. So they do have a tutorial like all the other Zooniverse demonstrations we've given you, and I will go through certainly the first one. Like I said, I think I'm gonna do the second one in a separate show for 2 reasons. I want to understand it better, and it's the length of time. I know for some of you it's quite late. All right, so let's see. Definitely read all this. What are they going to do with the results? And we talked about the timeline, of course. Let's see. Oh, so with this, they can calculate the redshifts and use them for apparently a number of projects. So that's always great when it will help them with more than one thing. I always say twofer.
Yeah, well, and for projects that they've got going now and future projects that they don't know about yet. I mean,
yeah,
you're creating a massive data for them that someone clever is going to figure out something else to do with that data.
Yeah. And I think they talk, let's see, confirming emission lines. We will also be able to estimate important properties related to these galaxies, like the rate at which they are forming stars, what their chemical composition looks like, and how their central supermassive black hole behaves. From there, we can address questions like how galaxies and their surrounding gas are related to the large-scale structure of the universe, how supermassive black holes contribute to their galaxy's evolution, and dark energy drives the acceleration of the universe's expansion. Let's see what else we have here.
Oh, and here it goes.
Oh,
I think there was another camera headed to the L2 point.
Oh.
Well, the Europeans have one that's up or getting to its point, but they did some first light pictures out of it. And
I heard about that.
yeah, and they don't have everything.
Oh, you sent me a
tuned
link.
up. Yeah, they don't have everything tuned up yet. But even the first light pictures are pretty decent.
Yeah, that sounded really exciting. I haven't read the whole thing yet, but really looking forward to learning more. All right. And anybody can help. Scientists, non-scientists can join the team. We hope our project is especially accessible and attractive to those who aren't trained professionals. And I think that's kind of good because you'll see stuff that the scientists won't. Because, of course, the scientists know all the things and what can't be possible. And you will sit there knowing nothing and you'll find things that are, you'll help make discoveries. All right, how to get started. And here it is. I think this is the video that tells you first part, second part. So you want to select task 1 or task 2. I recommend starting with task 1, especially since I think it's pretty easy to understand. Let's see. And I would read the tutorial once you're there. Oh, you got another?
Oh, yeah. Yeah, the European vehicle is Euclid.
Yes, that's right.
It's a survey instrument, yeah.
That's right. Very cool. Thanks, Don. Yeah, so, well, and I have this up. I think it's the classified tab, and then go to the 2. But here's a good way to learn with the video, and they have a tutorial as well. Let's see what else we have here. Join us and make important measurements using state-of-the-art astronomical facilities on the ground and in space. Happy wrangling. Isn't that great? I love it. All right. So here we are with task number 1. And it's kind of short. We often have more of these little dots at the bottom, which means there are more panels to look through. So I think this is very, very well done. This whole project seems to be very well done. It doesn't surprise me at all because it is funded by NASA, and you'll see the team. It's a pretty big team. I think they're doing a great job. So let's see. They want you to pick out emission lines and absorption lines in the spectrum. You want to be able to visually distinguish between them versus the noise. This tutorial will walk you through the steps, answer the questions, and identify the real features. The full spectrum in the top panel is there to guide you. We focus on the zoomed in panels below where you can see. And you can see that the full one here and these zoomed in panels below. All right, let's go to the next one. And here's kind of a typical peak with its corresponding bright spot. A real emission line looks like a peak in the spectrum that stands out strongly against the noise. Like this example, the 2D spectrum dark panel along the bottom, that's here, this bottom part with the little bright spot, can also help you pick out features like emission lines. An emission line in the 2D spectrum will look like a bright spot. And in the second step, in the second step, you'll be asked to draw boxes around. Oh, and that's still in this task 1. All right. If you see more than one spectrum, there may be more than one object in the region of interest. I saw a comment over there.
Yep. Cliff. Oh, I mean a new satellite probe. Astra, or Don, just answered what I was talking about. Yeah.
Very cool.
That's the Euclid, yeah.
Yes.
Astra says, this is a very interesting project. I'm going to try it too. It is very well written. We can work on spectrum like any jump cannon. Like any
jump cannon, yes. Yeah, I really like this. And I'll demonstrate a couple of the actual the things that you're doing, the tasks that you're doing. All right, so let's see. We're interested in the spectrum that corresponds both 2D and 1D. And that's you see the peak here, and you see the little bright spot underneath it. if a bright spot doesn't line up with the peak, or if a peak doesn't have a corresponding bright spot, that might not be the right spectrum for our galaxy, and you should not classify that as a real line. And you'll see again. I'll do a few of these. Alrighty. Now, if you got kind of like noise like this, you don't have. Oh, this one isn't. I'm sorry. You see the gaps? You've got 3 of them here. 1, 2, 3. Although this kind of looks more like regular noise to me, although you get here and they do kind of spike really predominantly. They're prominent here. This one I didn't think is quite so prominent, but it has the gap. So this is an absorption line.
Oh, one way to look at it is to take lines that go around, that go through the peaks of all of the smaller stuff, and then the bottoms of the troughs of all of the smaller stuff, and see what pops out above or below. And that gives you that also gives you a clue. But that line down below is really telling.
Yeah, the gap is for the absorption line and the little bright spot. It is Saturday afternoon for you, I know.
Yep.
All right, so let's see. On the 2D spectrum along the bottom, it looks like dark spots. I call it a gap, interrupting the bright spectrum. We also ask you to draw boxes around the absorption lines in the spectrum at the top, and that's this part here, the graph part.
Right.
All right. So, and they show the boxes, and in the video they actually have someone creating the boxes and adjusting them. In fact, these are probably not quite right, because see the gap between the top of this box and the top of the peak. They want you to bring that right to the peak. So you are confining this to that exact spike itself. Yeah. All right.
Gives the computer someplace to look.
Cool. All right, here's an example of a panel you might see with emission lines present. The task asks you to identify any features you might see by drawing boxes around them. You don't need to draw around the full spectrum. Just in these smaller. Oh yeah, that's this one here. Don't worry about that one. Just look at these panels that zoom in and draw your boxes in those. So let's see, just in these smaller panels, using both as a reference should help you pick out features. Notice how in this panel, the emission lines stand out both in the 1D graph as peaks and in the 2D image below as bright spots. Again, that's that peak with its bright spot. So if you had some kind of noise here that was maybe jaggedy and it didn't have a bright spot here, probably not the right thing. They're not looking for that. Yeah, we got another comment?
Yeah. Oh, sorry. Few was when I saw the story. Okay. Oh, so you haven't been knocking them back this afternoon. That's good to hear.
All right, let's see. As long as you think it's real, mark it. Put a box around it, whether it's an emission or an absorption line. And if there's something wrong with the data and there aren't any features, then the answer is I think there is something wrong. So you've got a couple of choices. We'll see that over here when we actually go do the task. All right, so what's this one? You may see objects with no spectral lines in any panels. In other words, no gaps, no bright spots, and this is all just jaggy. There's no, well, this kind of looks like a peak, but there's no corresponding gap here. Certainly not very bright. It kind of looks like it because I can see it here, but it's not going to be an absorption line. They want a distinct bright line with a distinct gap. That's what you're looking for.
And they said earlier that you want the bright spot or the dark spot lined up with the peak.
Yes. Right. So if you don't see any, can't find any here, then you go to the next one.
Yeah, Cliff. No, not yet.
All right. And they talk about these being skylines, which is kind of interesting. And they reference the field guide, which we definitely talk about too. And they always have really good ones. All right. So.
Well, NASA does. Some of them.
Yes. Yes. Well, most of these projects are pretty good, I think. Yeah. But this one is especially good. Let's see. Yeah. I think that's pretty clear. All right, so they do reference the field guide there. If you're unsure, don't worry. We're looking at the overall responses. Again, they have a number of people. They didn't really say in this project, but there is going to be you're not really concerned about whether you get it right or not. It's just do your best, like always. And if everybody's answer is about the same, then they have confidence that that's that way. And if they're different, they'll take a look at it. All right, so make an educated guess. Move on to the next set. And the field guide has more examples. All right, and let's just do a task. So I think that's the fun part. All right, so what we have here, of course, is the full spectrum. And then you've got A, B, C, D, E, F, which takes parts of it. And you can tell because of the numbers and the way it looks, and also the different parts of it. Like, look at this big spike here. The great thing is, too, you can actually zoom into these. Oh, yep, there's the dot at the bottom, right? So you got a big spike, and you got a dot. I'm going to go ahead and go like that. And you can look at the rest. That kind of looks like noise or the skylines, like they were saying. And this one, there's probably a spike there, which means it's an emission. And then we've got probably nothing specific here, skylines or noise. Yeah, I think zooming in will really help. But I can tell already that there are, and they say right here, do you see any emission or absorption lines in the given spectrum? The next step, you'll be asked to draw boxes around these. So I definitely see some. I actually found a lot that there weren't any. And when I was, testing this out, checking things out, and I didn't see anything wrong with them yet.
And that's what I saw a few times when I'm doing them, is that, okay, nothing to do on this one, nothing to do on this one, nothing.
Nothing to see here, yeah.
I want to find one that I can show people.
So I'm really excited that we have one that actually does have, and it's kind of a crapshoot because I had to reboot the computer and I get a new one. It just happens to have emission and or absorption.
Yeah, section
lines.
B, right?
I would say we've got section B, and we've got something over here in section D. But
and maybe a possibility in E for.
Well, we'll zoom in and look. So first step, though, you want to click on it. Yes, I see something, and then hit the next down here. There's always a help if you need help, and in this case, they kind of have a pop up. Emission lines appear. So it's a bit of the tutorial again. It gives you more information. You can close that out if you kind of know. Do we have another?
No, I just moved the screen a little bit.
All right. So I'm going to go ahead and go with next. And then here it is. Click and drag a box centered around each visible emission or absorption line in the zoomed in plots on the bottom. So you're not playing with this part. You're going to play with these little boxes down here. Marked A to F, using one box for each feature.
Cliff says, want to get the new scope out and first align. But as usual, the clouds have formed their unusual defense from me seeing the night sky.
It's only 60 miles up and they're all gone. All right, so if you don't see a way, because right now I see the cursor, how it's a big plus sign, I can in fact draw a box. All right, there's an example. If I have lost that particular cursor, and I'll tell you when you zoom in, whoops, that's the wrong thing, sorry. I rotated it instead of zooming in. So you'll see lots of different things over here you can do. This is the zooming in. And of course I have to fix that box. So when I don't have that big plus sign, I have this other cursor, which means I can move it around and make it a little bit easier to manage the box. And you want to get pretty tight in. The video had a really good demo of this. So if you do not see your cursor, go ahead and click on this and you'll get that big plus sign back. But I am going to, let's see, this one is reset because I want to hop down here and see that cursor still there. If I zoom in, I think, whoops, sorry, did the wrong thing again.
That's better.
Sorry. You know it's live when. All right. See, now I want to move it because that other, well, I think I got a couple here maybe. Well, no, I don't think that one is.
What about the one on the very left side?
Over here?
Yeah.
Oh, yep, you're right. I didn't even notice that. And of course you can, let's see. You can kind of tell from this too, is like, which part is that? 7-1, what is it? Yep, somewhere near, oh, yep. And it is right on the edge. So this can help you. It's just this is where you're going to mark them. All right, and so I have my my cursor again, but I want to, let's not do it again, zoom in, and it is a little complicated because if you still have that cursor, it makes it hard to move this to the position where you can mark it. So now I don't have that cursor anymore. I got to pick it up again. See, it's there. And Jeff's right. I'm going to go ahead and, I didn't even catch that one. Thank you. It's a little bit hard to tell where the bottom of that's going to be.
Right, yeah.
But I think I'm going to do that.
Mm-hmm.
And again, enough people are trying this that they'll get enough, accurate that we don't have to worry about it too much. All right, so. And if you don't like where it is, you got this little X here. You can get rid of it. But I'm going to tighten that up just a little bit. I think that's a good box for that one. All right. Let's go see if we have anywhere else. This kind of looks like noise to me. And I don't see any of the spots here. How about absorption lines?
Zoom in. You might
let's zoom in.
Oh, you didn't rotate it.
No, I'm catching on. Oh, there might be. No, I don't think it is.
So what?
It's
Did
not.
they say what it is when the lines, when that has bright lines down there?
No, I didn't see anything about this kind of smeary bright lines there. And I think we have another comment. Do we got?
Yeah. Cliff, didn't you know that telescopes are natural rain attractors? Damn, it works down here.
All right.
Unfortunately, it does not work in Southern California.
No. Okay, so this one here takes it back. I think we might have them all. Let's see. Well, what happened to this thing here? Oh, that's that. Okay. So we got one. I'm just going to count 1, 2, 3, 4. 1, 2, 3. Oh, but we found out this one wasn't really.
Yeah.
It's not really an emission line. Okay. Or is it? Yeah, emission. All right, so I feel like I'm done. I'm going to go ahead and click on done. And then it presents you with a new one. Oh, we got quite a few more again.
Oh, and we've got definitely an absorption line too. Right there.
Oh, you think so?
Yeah, well, it peaks down.
All right, well, let's start here. We definitely have emission and or absorption lines. Go ahead and go next. And then we're going to mark them. So this is the task. It's not super hard. And see, I don't think that one's definitely not. Oh, that one might be. And I don't have the right cursor again, so I'll pick it up and just draw my little boxes. Let's bring that down a little bit. And I don't think this is. It kind of looks like one, but there's no gap, right?
Yep.
This one's definitely got a little bright spot with it. So let's go there. All right. I'm going to check out the whole thing again. Yep, we've got a number of them here, at least 3. And then in C as well. Let's zoom in. And
maybe an E.
All righty. So I got to pick this up again. Yeah, boy, those are good bright spots. I wonder if that means more shifted. There's 1, 2. That one might need to be fixed, but that's pretty close. Yeah, I'm going to move it. You can pick it up and actually shift it a little bit. All right, what did we decide? Over here, right? Here's the trouble. If this cursor is like this, I can't really move it. So, oh, maybe I can pick up this. Yep.
Oh, goodness.
Yep, I'm going to get rid of that. Whoops. I'll pick up this cursor again, move it, and I can actually grab this thing and do what I want with it. So I'm going to do it that instead of getting rid of it.
Oh, we might have an absorption line too.
I think we do. All right. So, yeah, I would call that an absorption line.
Has definitely a dark spot underneath it.
Yep.
Oh,
there's something here too, but see, it's got a flat bottom, and they actually talk about that in the field guide, I think. And they've split this up between the task 1 Although this says task 2. I thought it was task 1 on the top and task 2 on the bottom. It's mostly split up that way, but I think if it's got this this kind of flattened, that's not going to qualify. But absolutely go. There's quite a lot here, so I don't think I want to go through too much of it. But they talk about all the different things, keywords, examples. But I think it's kind of nice to give you this demonstration here too. This one does not look like it has.
There's no bright spot.
No bright spot. Yeah. Let me go ahead and zoom out again. What did we say? We said, oh, we got something in here, right?
Mm-hmm.
All right, let's get the right cursor and move it along and go ahead and get right up in there. Oh, I got like 4, I think, right?
Yeah.
Okay, let's pick up our box and draw our lines. I'm going to tighten it up a little bit there. All right, that's 1. Oh, wait, here's another one.
Yep. See, you can see the bright spot down below.
Yep. Mm-hmm. That's a really big bright spot. Let's see. So you can definitely see how this is pretty good project. Whoops, I kind of don't like where that is.
I think you're not going to make it look pretty.
Well, yeah. I would just say do your best. It's pretty small. Oh, that's all right. I think that's okay. Did we get them all? Let's see. I'm going to go with 1, 2, 3, maybe 4 there, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 10. See anything else, Jeff?
Did we look at section F? Because that looks like a really deep one.
Let's do that.
Also, section C, I'll want to take a look at here.
We did C.
Yeah, I know.
There's C.
Look at the trough. It looks like there's 2 bottom peaks.
This thing here?
Yeah, and then the one next to it right there.
Oh, I see. I think you're right. All right, so it's gonna overlap a little bit.
Uh-huh.
Ugh. Let's move this side in a little bit. What do you think? Good?
Yep. Yeah,
all right.
You might want to bring the top up a little bit so that it meets the center line. Yeah. Yeah, just bring it up because even with the other one, because it looks like it starts on the other side.
Oh, I see.
Yeah.
Like this.
Yep.
Okay. Oh, like that?
Yeah.
Oh, okay. Very good. I did not think about that. All right, so I'm going to go ahead and move.
And you see there's no corresponding bright spot underneath.
No. No, it's a good peak, but not.
And they say that they said it earlier that if you saw a peak, but you don't see a bright, and there's a bright spot, but it's not underneath it.
Yeah.
Then they're probably looking at 2 different things.
Yeah. So I think we might be done.
Okay.
And definitely here again, if you want some help, click on the link and they will tell you. Drag your cursor, create the box. And I'm going to go with done. So that's basically it. Oh, let's do this one because I don't think I see any. Nothing. Well, look at that. What is that? That's an absorption line?
Absorption, yeah.
All right. So you get the idea. If there aren't any, go ahead and click on the can't find any here. Mm-hmm. If it looks funny, you think something's wrong, click that one. And then it's simple. Just go with done. When you have the first one, then you go into drawing the boxes. All right. What else do we have here? Yeah, this is the second task. And yeah, I'm going to look into this some more because I got stuck at the one point and I'm like, yeah. And I see we're already in an hour. What else do I have here? Oh, as always, talk. So if you really like forums, this is a good place for you. Oh, I was going to show you the team. Oh, shoot. That's a good one. And collections. Yeah, I totally blew it here.
I'll just find one of those.
Yeah, because this it's really good. I forgot I was going to go through the team, education, FAQ. Let me go talk about the team because this is kind of cool. This is Dr. Cardal Tepe, and she has a bunch of students. So it's kind of cool. So she's the lead. She's an astrophysicist, and every one of the other people on the team is a student of some sort, postdoctoral fellow, PhD student. Isn't that awesome? Looks like a great group of people, and of course they're going to be enthusiastic. I mean, this is what they're doing for their education. So yeah, very cool. Let me go ahead. Education. Oh, always learn more about Keck, Spectra, Redshift. Yeah, this is where this gets real meaty and crunchy. You can actually look into this quite a bit. Lots of rabbit holes to dive into. What is citizen science? What is the goal of the project? We kind of talked about all that already. And the demonstration, the task was kind of showed us too. Oh, yeah. How to automate. Well, yes. But they're not quite the same as a person. They do very well on the brightest things. However, not too much subtlety. Human visual inspection is still necessary. I'm not an astronomer. Doesn't matter. Yeah, again, don't worry about too much because there's a bunch of people looking at it. Doing it right? Yep. Don't worry about it too much. Oh, we got another comment.
Jamie. Fun cheer, guys. Have a safe and healthy weekend.
Well, absolutely. Thank you, Jamie. Glad you enjoyed this. All right. Other responses? Yeah, definitely delve into this. There's a lot here. There is a lot. I think, yeah, the collections. I think these are a little bit on the dull side because it's graphs. You know, they're graphs. I think doing the task is very fun. But looking at these collections might not be so much. All right. So that's it for this part. Let's bring us back.
There we are.
So far. All right. Go ahead, Jeff.
Okay, some stellar events this week, August 11th through August 18th. Globe at night continues through August 16th. In the north, we have Cygnus and Hercules. In the south, we have Sagittarius and Scorpius. And I think this is the first time I've seen it where there's no overlap between north and south. You know,
yeah, usually, a lot of them have been overlapped.
Yeah. So go out, get pictures, share them with the platform. And it is a great way to participate in actual citizen science because they are using these to measure the dark sky conditions in basically trying for worldwide, but you know, wherever they have people doing this, that's where they get it. I
really want to do this, but like this time I got sick. Have any of you tried this yet? I would love to. Well, I know Cliff has got clouds. Poor guy. Let us know.
You know, Cliff, when we point our telescope toward your sky, we don't see anything either.
All right.
Okay. Oh, yeah, me.
Yeah, you.
Quit talking and read out loud, right?
You know.
August 12th, moon rides high. And August 12th through 13th is a Perseid meteor shower, which peaks after midnight.
Go ahead and share.
Yeah. Okay.
Go ahead and share. Share.
Oh.
There you go. We found this today on Facebook. How to see the Perseid meteor shower.
In 3 easy steps. Step 1, get up early, as some of the best showings are of the meteors can be during pre-dawn hours. Step 2, realize the sky is blanketed in thick cloud and you won't be able to see jack unless you live in the Arctic Circle. Step 3, go back to bed and look at photos of the meteor shower on the internet.
All right.
As other people got to be able to take shots. Okay.
Back to us. A little joke there.
Yep. Okay. It ranges from July 17th through August 26th, and peaks this week August 12th through 13th. The best time to observe is after midnight. It radiates from Perseus in the northeast, which hence the name Perseid meteor shower.
Yep.
Peak rate per hour is 50 to 90, so 1 to 1.5 per minute. So that's pretty decent.
Mhm.
Still seems really slow. Oh,
You don't feel like it when you're out in the field. Yes. Did you get that one?
yeah. Cliff says, an interesting subject, I must say, but I hope to send you some pictures as soon as I can from the new scope.
Yay.
Saturn was fantastic, just looking.
Yay, very good.
Yep. Cliff, get better, guys, and take care.
Thank you, Cliff. I'm working on it.
Yeah. Oh, and Cliff.
One more.
Jeff, we have to have a little talk. Ha 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 ha.
Oh, the funny
It's an
bit.
X-ray telescope, Cliff. The moon is 26 days old. It's a very thin crescent and doesn't make an appearance until a few hours before sunrise.
Yeah, go ahead and share because I got the. Of course, this is the Farmer's Almanac. You can set it to the month and the year. You can see it. Sometimes these a big moon will interfere with your meteor shower, but this time, nope. We've got a very thin crescent, and the new moon is on the 16th, so it's going to be good for this particular meteor shower.
Mm-hmm.
It varies by year.
There we go. August 13th, Venus is in inferior conjunction, which just means it's between us and the sun.
Mm-hmm.
August, or near the sun, but inbound of us. August 15th, Venus and the moon are in conjunction.
Yeah, start watching for a deal on the old Farmer's Almanac. There's going to be a new one published on August 29th. Sorry, this is the one I'm talking about. This is the one I liked a lot. Of course, Dawn has a favorite. I think it's a different maker, though. It's not a Farmer's Almanac.
Yep. Okay. August 16th is the new moon. Great time to go out and observe. And the moon is at apogee.
Apogee, farthest away, I think, right?
Mm-hmm. August 18th is our Friday night show. Brown dwarf something or other. We'll explain shortly. Find us at Fridays at 9 p.m. Pacific time on the Everyday Spacer Facebook page and the Everyday Spacer YouTube channel. And Mercury and the moon are in conjunction, and Mars and the moon are in conjunction, which probably means that Mercury and the moon and Mars are in conjunction.
Yeah, they're all together. Yes. So if you or someone you know has done something interesting involving space exploration, science, astronomy like that, we'd love to share a live. Join us again next Friday, August the 18th. What we're going to do is we're going to try for that brown dwarf project, Backyard Worlds, Cool Neighbors. If it's done, Jeff will, yes, we're going to be watching. Jeff will do a crunchy episode about brown dwarfs. Yeah,
basically I found enough stuff about brown dwarfs that I just got to reading about them, and so it just, if we don't do the Zooniverse project, we'll just talk about brown dwarfs. If we do the Zooniverse project, I'll talk about brown dwarfs in detail another time. Yeah. Tonight's trivia question: what's the largest mass a brown dwarf can be? Join us again next week. We'll answer and see if you got it right.
Yeah, if you like the trivia, we'll keep doing it. If you don't, we'll stop. No problem. All right. Any more comments?
No.
I think we got it. And let's do a shout out. Hey, Cliff. Hey, Janie. Dawn. Scott. Thank you all for joining us. Daniel. Really, really appreciate that. You make this a very fun show. Mm-hmm. And you always enhance what we know. And we are so grateful. All right. I think that's it. Anything else from you?
Nope.
We'll watch for your comments too. Thank you so much for tonight's. And yeah, have a great week, folks.
Well, I did start having ideas for a game called Redshift Wrangler.
Okay.
Whole bunch of guys in red shirts running around trying to find ways to kill themselves, and you have to wrangle them. And you know, when you run out of the last red shirt, you're done.
Okay. Daniel had something to say.
Live long and prosper.
Okay, thanks, Daniel. And with any luck, we will be over this creeping crud, my mother always called it.
You know, Spock never said that to a red shirt. I wonder why.
Live long and prosper. Good night, folks. Have a good week. Bye.
Bye.